Welcome everyone. Today I will discuss Markov decision processes and demonstrate how they can be solved using the discounted cash flow approach. The example we will study is a simple two-state Markov decision process with a discount factor equal to 1/2. The objective of this presentation is not only to find the optimal policy, but also to understand the logic behind the solution methods and see how different approaches lead to the same result. Before studying Markov decision processes, we need to understand Markov chains. A Markov chain is a mathematical model used to describe systems that move between different states over time under uncertainty. After introducing the main concepts, we will examine two important methods for solving Markov decision processes. The first method is policy iteration, which improves decisions step by step. The second method is linear programming, which converts the problem into an optimization model. Finally, we will compare the results obtained from both methods. A Markov chain is a stochastic process that changes from one state to another over time. Its most important characteristic is the Markov property. This property states that the future depends only on the current state and not on the sequence of events that occurred before. For example, when predicting tomorrow's weather, we only need today's weather condition and do not need information from several days ago. This assumption greatly simplifies analysis and makes Markov models useful in many real-world applications. To describe movement between states, we use transition probabilities. A transition probability represents the likelihood of moving from one state to another during a single time period. For every state, the probabilities of all possible future states must add up to 1 because one of those outcomes must occur. The weather example shown here illustrates this idea. If today is sunny, there is a certain probability that tomorrow will also be sunny and another probability that it will be rainy. These probabilities define the behavior of the system. Instead of listing probabilities separately, we organize them into a transition matrix. Each row represents the current state, and each column represents a possible future state. Every row must sum to 1 because it contains a complete probability distribution. The transition matrix is extremely important because it fully describes the dynamics of a Markov chain. Once this matrix is known, we can analyze future behavior, calculate long-run properties, and predict how the system evolves over time. A Markov decision process, or MDP, extends a Markov chain by introducing decisions. In addition to states and transition probabilities, we now have actions and rewards. At each state, a decision maker chooses an action. That action influences both the reward received immediately and the probabilities of future transitions. The discount factor represents how future rewards are valued compared to current rewards. The goal is to find a policy that maximizes the total expected discounted reward over time. To illustrate the solution methods, we consider a simple problem with two states. In state 1, 3 actions are available, each providing a different immediate reward. In state 2, there are 2 possible actions. The transition probabilities associated with these actions determine how the process moves between the 2 states. We will solve this problem assuming a discount factor of 0.5. Meaning that future rewards are worth half as much as immediate rewards. There are several ways to solve an MDP, but today we focus on 2 classical approaches. The first is policy iteration. This method starts with an initial policy, evaluates its performance, and repeatedly improves it until no further improvement is possible. The second approach is linear programming. Here, the Bellman optimality conditions are converted into a set of linear constraints and an objective function. Although these methods are different, they should produce the same optimal solution. Policy iteration is one of the most widely used exact solution methods for Markov decision processes. The procedure consists of 2 main steps. First, we evaluate the current policy and calculate its value function. Second, we improve the policy by checking whether another action would produce a higher expected reward. These 2 steps are repeated until the policy no longer changes. At that point, we have reached the optimal solution. To begin the algorithm, we need an initial policy. Our starting policy chooses action 1 whenever the system is in state 1 and action 2 whenever the system is in state 2. This policy is simply an initial guess and is not expected to be optimal. One advantage of policy iteration is that it can start from any feasible policy. The purpose of the first iteration is to evaluate this policy and determine whether better decisions are available. Once the initial policy has been selected, we can construct the transition matrix and reward vector associated with that policy. The transition matrix is formed by selecting the transition probabilities corresponding to the chosen actions in each state. Similarly, the reward vector contains the immediate rewards obtained from those actions. Together, these two elements completely describe the behavior of the system under the current policy. The next step is to use them to calculate the value function and determine how much reward we can expect in the long run. Policy evaluation measures the quality of the current policy. To do this, we use the Bellman equation, which relates the value of a state to its immediate reward and the expected discounted value of future states. Rather than thinking of the equation as a formula, think of it as a balance between present benefits and future opportunities. By substituting the transition matrix and reward vector into the Bellman equation, we obtain a system of linear equations that can be solved for the value function. After solving the system of equations, we obtain the value associated with each state. The value function tells us the total expected discounted reward that can be earned when starting from a particular state and following the current policy forever. For this initial policy, the value of state 1 is equal to 2, while the value of state 2 is equal to 0.4. These values provide a benchmark that will help us determine whether alternative actions can produce better results. Now we begin the policy improvement step. For state 1, we evaluate all available actions using the value function we just calculated. Each action is assessed by combining its immediate reward with the discounted value of future states. When we compare the results, action 3 produces the highest expected return. Because it performs better than the action currently used in the policy, we replace action 1 with action 3. This means that the policy can be improved in state 1. Next, we repeat the same process for state 2. We calculate the expected return for each available action using the current value estimates. The comparison shows that action 1 generates a larger expected discounted reward than action 2. As a result, action 1 becomes the preferred choice in state 2. Since improvements were found in both states, a new policy is created and another iteration is required. After the improvement step, the policy changes from the initial policy to a new policy consisting of action 3 in state 1 and action 1 in state 2. This updated policy reflects the best decisions identified during the improvement stage. Using this new policy, we construct a new transition matrix and reward vector. We then perform another policy evaluation to calculate the corresponding value function. As expected, the resulting values are significantly higher than those obtained under the initial policy. Using the new value function, we once again evaluate all actions available in state 1. The purpose is to check whether an even better action exists. After performing the calculations, action 3 still provides the highest expected return. This means that no change is needed in state 1. The action selected in the previous iteration remains the best available choice. This is a strong indication that the algorithm is approaching convergence. The same verification is performed for state 2. Once again, action 1 produces a higher expected reward than action 2. Since the preferred action does not change, state 2 also remains unchanged. At this point, the improved policy is exactly the same as the policy from the previous iteration. Because no further improvements are possible, the algorithm has converged and the optimal policy has been found. The final result of policy iteration is the optimal stationary policy. The optimal decision is to choose action 3 whenever the process is in state 1 and action 1 whenever it is in state 2. The corresponding value function indicates the maximum expected discounted reward achievable from each state. An important observation is that the algorithm reached this solution after only a small number of iterations, demonstrating the efficiency of policy iteration for solving Markov decision processes. We now solve the same problem using a completely different approach. Instead of improving policies iteratively, we formulate the problem as a linear optimization model. The decision variables are the state values. The Bellman optimality conditions become a set of linear constraints. The objective is to find the smallest value function that satisfies all these constraints. Although the mathematical framework is different, the optimal solution should be identical to the one obtained through policy iteration. The first step in building the linear program is writing one constraint for every state action pair. For state 1, there are 3 actions, so we obtain 3 separate constraints. Each constraint represents the Bellman inequality associated with a specific action. Conceptually, these inequalities ensure that the value assigned to a state is at least as large as the return generated by any available action. Together, these constraints define the feasible region of the optimization problem. We repeat the same procedure for state 2. Because state 2 has 2 possible actions, we obtain 2 additional constraints. When comparing these constraints, one provides a stronger lower bound on the value of state 2. In optimization terminology, this constraint is more restrictive. As we will see shortly, the tighter constraint plays an important role in determining the optimal solution and identifying the optimal action in state 2. At this stage, we have all the components needed for the linear program. The objective function minimizes the sum of the state values. The constraints come directly from the Bellman inequalities derived earlier. The feasible region consists of all value functions that satisfy every constraint. The optimal solution will be the point within this region that minimizes the objective function while remaining consistent with the dynamics and rewards of the Markov decision. Process. To solve the model efficiently, we identify the most restrictive constraints. These are often called binding constraints because they determine the location of the optimal solution. The tighter constraint from state 2 is substituted into the state 1 inequalities. This allows us to express the problem in terms of a single variable and compare the resulting lower bounds. By examining which action generates the largest lower bound, we can identify the action that ultimately determines the optimal value. After substitution, we evaluate the lower bounds generated by each action in state 1. Action 1 produces the weakest bound. Action 2 produces a stronger bound. However, action 3 produces the largest lower bound and therefore becomes the dominant constraint. This result suggests that action 3 is the optimal decision in state 1. The analysis also confirms what we observed earlier during the policy iteration procedure. Once the binding constraints have been identified, we calculate the optimal values of the states. The next step is verification. We substitute the solution back into every constraint to ensure that all conditions are satisfied. Notice that some constraints hold exactly as equalities, while others contain slack. The constraints that are tight correspond to the optimal actions. The constraints with slack represent actions that are not selected in the optimal policy. Let us conclude with the main lessons from this presentation. We began by introducing Markov chains and the Markov property, which states that future outcomes depend only on the current state. We then extended this idea to Markov decision processes by incorporating actions, rewards, and decision-making. Next, we solved a 2-state MDP using policy iteration and linear programming. Although the methods are very different, both produced exactly the same optimal policy. This consistency demonstrates the strength of the underlying theory and confirms that the optimal strategy is action 3 in state 1 and action 1 in state 2. Thank you for your attention.